Okay, we're going to look at, we've done previously in the earlier sections of Chapter 3 applications of quadratics, so now we're just going to do a couple more applications where we're going to specifically solve for the zeros. Or solve our special type of application with the square term. Alright, so solving application problems with the quadratic cases. I suppose that we have a free-falling object. So a metal ball is dropped 100 feet from a water tower. Its height in feet above the ground is t seconds. In t seconds is given by 100 minus 16t squared, which 16t squared has to do with the pull of gravity. It's the only thing we assume is playing on the ball. Determine how long it takes for the ball to hit the ground. Alright, so the solution to this is we want to, this gives me the height, and so the object, so again, we're on a tower, we drop the object down, and we want to know the time it takes for it to go from the top of the tower, the 100 feet, all the way down to the ground. Well, the ground would be 0 feet above the earth, and so that would be when my height is 0, and so that's the first thing you do, is you set it equal. So you are solving for the 0. When is that equation, when is that height at a 0? Alright, so 100 minus 16c squares is what we're solving for. We find our time. And so we solve that. And since it's only getting a t term, this is actually our special case where we solve for the square term and then use the square root property. So I'm going to move the 16t to the other side because I don't like negatives. I typically lose negatives. So I'm going to move the 16t over to get positive 16. So I've got 100 left on the side. 16t squared on that side, divide by my 16. Alright, and so this comes out to 6.25 t squared. Now, we usually do plus or minus, right? Plus or minus the square root of 6.25 equals my t. But remember, time is always positive, just like distance is always positive. And so we only want the positive of it. So we will leave off the plus or minus in this case. And so it takes exactly the square root of 6.25, which comes out to exactly 2.5 seconds. 2.5 seconds to hit the ground. Alright, so it takes it 2.5 seconds to travel that 100 feet. That's what it takes, 2.5 seconds. So once the ball is dropped, it takes 2.5 seconds to reach from where it was dropped 100 feet up to 0 feet up when it hits the ground. Alright, next example, which actually this is going to be a tougher case because I have to set up. This is actually a common example. If you're going to go on to calculus, this is one of those that we use in calculus all the time. Now we solve it with calculus and we'll usually get another variable in there. We won't know how many inches it is cut. Alright, but we will set this up with the algebra in this case. And the hard part about these sometimes is the setup. Alright, so you have a box that's being made when I cut out little corners, right? So I'm cutting out a square, a 2x2 square at each one of my corners of the rectangle. Alright, this piece of cardboard, one side is 16 inches longer, so the length is 16 inches longer than the width. Alright, the box is supposed to have a volume of 224 cubic inches, so we want the volume to be 224 inches cubed. Alright, how big of the box do we need? What's the dimensions of the cardboard? And so what I'm going to do is, well, again, I want the volume of this box. And I know, I'm going to call the longer side is the length, right? The shorter side is the width. And I know the length is 6 inches, even when I make my cuts, because I'm making the same cuts, it's still, when I cut it and make the box, the length is still going to be 6 inches bigger than the width, even after I make my cuts. And so I'm going to let the width be the smaller amount. So my width, which I'm going to let be dx in inches. The length then is 6 inches longer, so x plus 6. Alright, so that's x plus 6. The height is my cuts, right? That's the part that we're folding, and so 2 is the height, because we're going to fold up on those 2 inches, and so the height is 2 inches. Those are the cuts. And what you do in calculus, actually, you usually want a maximum or minimum volume and you figure out how much you have to make those cuts are. Right? But we're going to do it from, we don't have calculus yet, so we're just going to solve it with algebra. We know what the cuts are. We have 2-inch cuts. We want a certain amount of volume, so we have to know how big a box we need to start with. So there's all my pieces, right? Volume is length times width times height. Length is x plus 6, width is x, height is 2, and so I plug those in. Volume is x plus 6 times x times 2, and I want my volume to be equal to 224. All right, so 224 is what I want my volume to be. I'm going to go ahead and multiply this out. So I'm going to distribute my 2x inside, and so I'm going to multiply 2x, so I get 2x squared. 2x will give me 12x. So again, I just multiplied by both the x and the 2 inside. I distributed the x and the 2. And now this is the equation I want to solve, right? I want to solve this for x. And so I'm going to solve it by, again, using one of my ways to solve it. First step is always to set it equal to 0. And so first step is to move that 224 to the other side. So 0 equals 2x squared plus 12x minus 224. And now it's up to you. This one does factor. Right? It is factorable. If you want to solve it by factoring, you can pull out a 2 and factor it that way. You can solve it using the quadratic formula. You could graph it, find its zeros. And since I'm going to assume most students will do the graphical method, that's the method I'm going to use. So I'm going to graph and find its zeros. And again, I already showed you how to do that, so I'm just going to generically draw the graph here. Now, what you have to be careful of in this case is the window is fairly large. Alright, because of this, it's going to be large, so I do have to zoom out. When I graph at a standard window, it won't work, and you can use the table to kind of help you out with it. So again, I go about 200 up, left and right, so is what I'm doing, and it should give me a fairly decent window. You still need to make it bigger, again, zoom out. Actually, I'm just going 200 up, 200 down. This is still going to be negative 10, this is going to be positive 10, so there's my window. Alright, it does cross at 2 points, so there's my y-axis, there's my x-axis. And so, remember, x represents my cuts, or not my cuts, my width. Right, which is a distance, right? It's the width of my box. Which means, over here, this is negative. I don't want the negative one, so I'm only going to solve for this one. I'm only going to find this 0. Right, that's the only one I want. I don't want the negative 0 because it doesn't make sense. I can't have a negative box. And so I solve for that. And so again, remember, on your calculator, you've got to go to the left of it, to the right of it, and then guess, and it should give you your 0 at 8. And so my answer is, and so if you use the factoring method or the quadratic formula, you'll get 2 answers out. One of them will be positive and one of them will be negative. Negative is what we consider an extraneous solution. We throw it away. We don't want it. It doesn't make sense to the application because the application would only involve the positive real numbers. And the only positive real number is x, is 8, for x is 8. And so the answer is 8. Which, again, is only part of the answer. I want to know, find the dimensions of the box for the piece of cardboard. And so I already know this has to be 8 inches. This has to be 8 plus 6, so that's 14, right? So my box, so that's my box, has to be 8 inches by 14 inches, but that's not what the answer is. Remember, I want to know what my original cardboard box was before I made the cuts, right? I want to know, well, the original box before I make the cuts, what's its width? What's its length? Well, remember, I made cuts of 2 inches on both sides. And so my original box was 4 inches longer and wider than what my box with the volume I wanted in it. Right? So the box with the volume has an 8-inch side and a 14-inch side. But remember, in order to get that box, I had to cut 2 inches on both the sides with the length and both the sides with the width. And so altogether, we cut 4 inches off, right? We cut 2 inches here, cut 2 inches here, so we cut off 4 inches. And so the width of the original cardboard piece has to be 4 inches bigger, and so the width was my 8 plus 4 inches, so 12 inches. And the length has to be 14 plus 4 inches, and so 18 inches. And so the answer is the cardboard box has to be 18 inches by 12 inches. All right, that's my final answer. All right, so the piece of cardboard write out my word, piece of cardboard, needs to be 18 inches by 12 inches in size in order to make it cuts of 2 inches in the corners folded up and to get a volume of 224 cubic inches total. Alright, so that's how big of a piece I have to start with. Alright, I have to start with 18 inches by 12 inches. Alright, just so that you know, we are skipping 3.3, which is on complex numbers. If you're curious, you can always look at it on the MyLab. But everything we do in this class, and everything that you should be doing in the classes after this, so if you're going on to finite math, or calculus, business calculus, or statistics, all of those math classes are based on real number values. We don't use any imaginary numbers. Right? You'd only use imaginary numbers if you were going on past Calc 1. Alright, and so we were going to skip over there because most students who are in this class are not doing that. But if you are, you might want to look that over. You won't see imaginary numbers till Calc 3 and some later math sections if you are going on. And by then, you'll probably have forgotten most of it anyway, and you'll have to be reminded in that class. And so, like I said, we skip the complex numbers in this class because most of you aren't going on to that. But if you want to look at it, you have the book. It's free to you. They have videos over it through the book. So you go to the multimedia library and look at the videos on 3.3. But I will not be testing you over it. I will not be covering it. Right? If you want to go over it on your own and learn it on your own, you can do that. If you are going to go on to, like I said, Calc 3 or beyond. Alright, we'll stop there.